Title of the presentation today is Introduction to Underwater Doppler Current Profilers, or more commonly called ADCPs. And as Frida introduced, my name is David Velasco, and I'm a product manager with Nortek. So let's get started. This over? Okay. So my objective here today, is just as it says here, is to make you a better ADCP operator, and by presenting you 4 core principles that are critical in understanding ADCP performance. Obviously, these are not the only core principles for ADCP performance, but these are the top ones, or at least some of the critical ones. And so if I could sum it up here, I think my job is to try to make your job easier today. Here's the agenda that we're going to follow. I'm going to give you a brief introduction to ADCPs. Then we're going to touch on the 4 principles that we will be talking about. I'm going to present them all 4 in the similar fashion, given a brief introduction, then followed by illustration, and then a practical application of those principles. And then we're going to open up the floor to some question and answer time at the end. So introduction to ADCPs. So current measurements are actually an essential function for a lot of different disciplines around the world. For example, flood control and flood mitigation, of course, is an obvious discipline that requires current measurement. Coastal protection, of course, another one. Climate change as well as weather prediction are both directly related to ADCPs, because global ocean current patterns are directly, of course, driving global ocean and climate change, and therefore, or related to, and therefore ADCPs, of course, are connected to these. And so of all of the disciplines and the function of current measurement, ADCPs are certainly one of the most widely used tools for measurement of currents. Now, I'm going to give you a brief overview of how an ADCP operate, and then we're going to dive in a little bit more into it. So ADCPs, as illustrated here, they operate by sending pulses of sound out of these transducers, which are, in this case here, these white little discs, and they transmit these pulses of sound outward from the instrument, and they propagate through the water. They reflect off of the particles that are in the water, and once they reflect off these particles, they generate an echo that is then traveled back towards the instrument. Of course, this happens very fast at the speed of sound underwater, which averages about 1,500 meters per second. Now, the frequency of the sound that comes back towards the instrument, it's either going to be greater than or is going to be less than the frequency that was sent out of these transducer. And this change in frequency here is what we call Doppler shift. Now, the Doppler shift is proportional to the speed of the water that is moving above the instrument or in front of it. Now, another interesting aspect of the ADCPs is that we listen to the return of the echo from these scatters in the water, from these particles in the water at different times, and that allows us to slice the water column into multiple layers within the water column. That allows us then to generate a profile over the course of the height of the water above the instrument, or below it if the instrument is looking downwards. And then finally, when we are able to do this by using more than one of these transducers here, then we're able to not only measure velocity in the horizontal, but also, both axes of the horizontal, but also in the vertical. So given really 3-dimensional current profiles. So this makes it for a very powerful instrument. So the 4 principles that we're going to touch base here today are the intensity of the acoustic pulse. We're going to talk about sidelobe energy, and we're going to talk about then profile and range, and then bandwidth and processing, which are 2 functions or 2 principles really that are very closely interconnected in ADCPs. Now, before I move forward, I just wanted to introduce you now to a short video that you're going to see in the screen. It's less than a minute long. And the video is actually a demonstration of somebody actually operating a flashlight at night in an open field. The light is actually, I'm using this because light is actually a very good analogy to sound, and it helps us to understand better some of these concepts because obviously we can see it. And so I'm going to start the video here. There's no sound to the video, and then we'll go talk about it afterwards. So I can see somebody just using a flashlight in the middle of a field, and there's different aspects to this that we will talk about during the rest of the presentation. And I hope you can, the video is actually moving in okay for you. We have a lot of participants in this webinar series. But like I said, I will have the actual screen captures of the actual video portions later on, so we can. So hopefully this again might not make too much sense for you at this point, but I'll try to explain here now. So the first principle we're going to be talking about is signal intensity. There are different names for signal intensity. This has been called everything from just the strength of the signal amplitude, RSSI, echo intensity. But the most proper way to call or to refer to a signal intensity is what we call SNR, or signal to noise ratio, which is provided in units of decibels. A key point here is that we really want to note, again, to go back to the overall objective here to try to make your job easier, is to try and understand how SNR changes with distance away from the instrument. So as we look here, we have a guy holding in a flashlight. Is what happens to that signal from the moment that it leaves the flashlight to the moment that it actually hits your target there at the far end? So in the practical application, as far as signal intensity is concerned, really learning how to read these what we call SNR graphs or SNR profiles is of great importance in operating ADCP. And if you learn how to read them, it will certainly make you a better ADCP operator. And so what I have illustrated here is just a simple graph where we have SNR in the x-axis and range or distance away from the instrument in the y-axis. This is basically relates to the distance from the face of the instrument all the way up to where the boundary is. And what you expect to see in a normal profile is just as I have illustrated here. You want to see a normal logarithmic decay. You want to have the signal to start strong, high SNR, decay logarithmic with distance. And then once you hit a boundary, in this case here is the surface of the water, you're going to get a very high peak. And then you're going to flatten out to a level what we call the noise level. And that basically relates to an SNR or a signal intensity that is below which we cannot really detect or no ADCP can detect the water movement. Or accurately, I should say. So the SNR tells you a lot of things about not only what's going on with the ADCP, but also what's going on in the water. As an example here, let me get rid of, there you go. So as an example here, what you get to see, these are 5 different graphs that I have plotted here, the original one that we started off with. Here's if the system was in open water, so you're not seeing any of that spike that you see in the surface. This is as if the instrument, for example, had one of its beams blocked. You would see a profile SNR graph that would look like this. If the instrument was in very clear water conditions, you would see a signal start strong at the beginning and then decay very rapidly towards the noise level. And if this instrument was in very muddy water, for example, you also see that strong beginning, but it would stay strong until you see a less defined peak, and then going down to the noise level. I know this is quite a bit of information thrown at you guys all at the same time. But again, the point is that as you learn to read these SNR graphs or SNR profiles, they'll be able to tell you not only how the system is operating, but it'll also tell you information about what's going on in the water column as well. The second principle that I want to touch base with you guys was what we called Sidelobe energy. Now, we think about ADCPs profiling or transmitting these beams of sound out of the instrument, like I mentioned earlier, and we draw them as very thin, sort of almost like the flashlight example that I showed you earlier. But in reality, they're not these pencil beam or as they're called, or very sharp focus laser. When in reality, energy is actually flowing in all sorts of different directions outside of the instrument. Most of the energy, of course, is focused along the central beam, but there is energy that escapes. And this energy that escapes is what we call the side lobe energy. So it's energy that it's outside of this main lobe here. This translates into two important aspects. The first one is that there's a region near a boundary where we cannot measure. And it also means that if there are objects near the path of the actual beam, that those can actually interfere with the signal as well, but not necessarily block it. So in the case of using the example of the flashlight that we use, you can see here very clearly, we have the main lobe of the flashlight, but you also get to see things around the area over here that are outside of this main lobe. Here again, you see the main lobe here of the flashlight, but you get to see things outside of it as well. That's the exact same thing in light here as it is in sound for us with this side lobe energy. So in a practical application of this principle of understanding side lobe energy is that a couple things to keep in mind are that, one, there's nothing to correct about side lobe energy once the data is actually collected. So if you have an obstruction in your beam, there's nothing that you can do to remove that once the data is collected. And it's also fairly difficult to accurately model and to actually predict. And because of that, it's actually best to try to minimize this in a pre-deployment sense. And Nortek recommends a 15-degree zone, or what we call keep out area, outside the path of the transducer. So here you have an illustration of one of our ADCPs, just illustrating where the transducer would be located, the width of the transducer, and then this area outside of it. So it makes a cone around each of the transducers, which we want to try to keep free of obstruction to minimize any potential of you having interference with the side lobe energy. And then, of course, during installation, if you are able to check the data, you want to see if the data actually, instead of a nice logarithmic profile like we had mentioned earlier, if you have any bumps or any other potential interference that you would see along the path of the beam. Now, as far as profiling range, that's the next topic or the next principle that I wanted to touch base on today. And the key thing about understanding profiling range is that sound, just like the light that we saw in the flashlight earlier today, sound is going to weaken with range, and it's going to do that. So there's going to be a limitation on how far the ADCP can actually hear the echoes that are bouncing off the different particles within the water column. And there are two main factors that contribute to this. The first one is geometric spreading. As illustrated here, basically the same intensity that you send out in the instrument gets spread out as those beams are spreading outwards away from the instrument. And so that means that with every increasing in distance, you have that same amount of intensity gets distributed over a larger and larger area. That's what we call geometric spreading. Second, there's an overall factor that I'm just kind of calling attenuation loss, and I'm sort of saying that it involves a lot of different aspects: the absorption of the sound by the particles in the water, energy leakage, like we talked about earlier with the side lobe. And so, to use the illustration that we had with the flashlight earlier, here you have, you can kind of see the main lobe here. You can barely make out the very last tree here, but the things that are closest to it are certainly, of course, our brightest. And that's the same thing for us in acoustics. As the sound propagates through the medium, in this case here for us, water, it gets absorbed, it gets scattered, it's spreading, And so you end up with getting harder and harder to actually hear from the farther and farther away that you go. And so in a great way to illustrate this is to take data, look at actually data. This is data coming from a 100 kilohertz instrument that we have called Signature 100 that happens to be in the Mediterranean Sea. And what I'm showing here is date on the x-axis and range on the y-axis here. This is a system that is deploying about 450 meters of water. That's the water surface right there. And this dashed line over here represents this profile over here in time. So again, it's very similar to that one that we showed earlier with the logarithmic decay that we see and a sharp peak right at the surface. Now, you also see that this period of time over here was actually during the daytime, and what you're seeing is that you have, due to plankton migration, you have a lot of scatters, you have a lot of particles in the water column here for the sound to reflect off. Now I'm going to move over to a different period in time. So this exact same instrument, exact same configuration, but now I'm going through a period in time where it's actually nighttime, and so the scatters, the plankton has actually migrated downward into the water column. And I'll go back here so you get to see better. But as you can see, this is the original curve that we had. Once you go to the different time, you see that now that curve has actually flattened out much earlier. So what this means is that in practice, just like it would be for just about any ADCP out there, the effective range of the instrument has actually been reduced, having absolutely nothing to do with the actual instrument itself, but having everything to do with what the water column is showing. In another example of this, or I say a more of a practical application, what impacts really the profiling range is not only the frequency of the instrument. In the case, the lower the frequency, the longer the range the instruments have. The amount of scattering, which means the particles that are actually in the water column, and of course the noise level really dominate what we're talking about. Because as if you can imagine, if this noise level here was higher in the water column, then that range would actually be shorter than what we had. This is an example here of what this scene in action. This is one of a Nortek Signature 55 in the Gulf of Mexico, operating down, looking from the surface, looking downward. And what you see is these alternations here of higher and long, or shorter and longer ranges are 100% related to what the distribution of particles in the water column here. And again, so the more that you learn about some of these principles and you learn how to understand them, the greater is going to be your ability to increase your data return. The last principle that I wanted to touch base with, and these are kind of really two that are very interconnected with each other, certainly within the Doppler industry, and that's the bandwidth in processing. I'm going to kind of group them all together, and I'm just going to call them ping type here. And there are three main flavors, I would say, of ADCPs or ping types out there that can be. One is what we call narrowband. Another one is what we call post-coherent, and then there's final one there's called broadband. I won't go into details of how these operate, just because this is beyond the scope of our presentation here today. But I do have them listed out in 5 different categories to help you understand a little bit better. So as far as range is concerned, narrowband generally gives you a better range, about 10% on average when compared to broadband. Broadband does give a fairly decent range, but post-coherent gives us by far the shortest profiling range. So the distance away from the instrument is by far the shortest with this type of ping called post-coherent. As far as velocity precision, the best one by far is what we call the post-coherent method, and that typically is about 10 times more than what broadband would be able to give you. The lowest of them, of course, is going to be the narrowband, which means that it actually requires quite a bit more averaging in order to get for a reasonable uncertainty measurement. As far as the maximum velocity that you can measure, narrowband gives you the largest velocity range that you can measure. whereas pulse coherent has a limited capability because there's a velocity range trade-off between the two. In short, the greater the velocity that you measure with this method, the shorter the range that you can actually do that. Broadband is a really nice compromise between the two, and offers you a very good sort of range and maximum velocity threshold between the two, between narrowband and pulse coherent. As far as power consumption, the largest power consumption of the three ping types or techniques out there is narrowband, because it requires the most amount of pings in order to get to a reasonable precision. And therefore, you're looking at about 30–40% more than broadband. Broadband actually has quite low power consumption. So it's really nice for very long-term deployments. Pulse coherent actually is the best in terms of per ping or per acoustic pulse that's transmitted. However, most pulse coherent systems are actually operating in very high sampling rates, which then kind of negates this ability or this improvement. And lastly, and from a more application perspective, as far as the spatial scales that you can measure, typically narrowband is used a lot in some large currents or large scale spatial currents. Broadband gives a very nice compromise between large and very fine resolution measurements. And then lastly, pulse coherent is certainly the best choice as far as small scale and turbulence measurements. So really, it's sort of a practical application here. As far as bandwidth and processing is concerned, really we want to think about having the right tool for the job here, right? So you can do things. So you want to make sure you match the instrument and the technique that you're trying to use with the actual focus of the actual measurement that you're trying to achieve. So things, of course, that you want to take into consideration are what is the required range for the system that you have, what is the data rate that you are required to have, the desired precision that you need for your actual measurements. You have to really think about that a lot in determining which of these methods that you're actually really going to use. Obviously, the scale of the currents, the available power that you have, whether it's in battery or if you're actually operating it online, and of course, lastly, budget is also factors into this equation. So again, just to wrap things up, I know I threw a lot of information at you. Hopefully, you can go back to this later on and kind of review some or ask questions. But just again, just give you some final words here. We've talked about signal strength, we talked about Sidelobe, profile and range, and bandwidth and processing. We have not talked actually about currents. And that's, you might be asking yourself, we're talking about ADCPs, why aren't we talking about currents? And the reason is that provided that you have these things in place, and that's really one of the big takeaways here, provided you have these things in place, then there's no reason why, or you really minimize the chance that there's going to be anything wrong with the currents. And so provided that you take care of some of these principles and you understand them and you learn and you put them into practice first, then time you'll be able to get very good quality data or current data from your ADCPs like illustrated here.